this is exam preparation, session 11. And what I'm going to do is question 28 and 29. So fundamentally for this series of the exam prep, obviously I'm going to keep adding in more and more videos as it comes. But for this initial series, we're going to be ending off with this. And the last two ones are essentially also equations of motion with an energy problem right at the end. Let's have a look at question 28. People are in a hot air balloon rising with a constant velocity of 3 meters per second. They throw a ball upwards at 3 meters per second relative to the rising balloon as the balloon passes 20 meters above the ground. Answer the following questions relating to the motion of the ball and the balloon. So, first of all, you have to say to yourself, okay, what is going on here? This is what's happening, isn't it? Right? The balloon is rising at 3 meters per second. There's a person standing in the balloon with a ball. So as it's going up, the ball in the balloon is traveling at 3, isn't it? If you're in a car traveling at 60 kilometers an hour, the car is traveling at 60, but so are you. That, incidentally, is where a lot of people who've got they have their children on their laps, and when you say to them, "But if you brake, no, it's okay. I'm holding my child." They don't understand that they actually can't. That the rapid deceleration, the force on that child is going to rip it out of their hands. It's a very dangerous pastime. It really is. I often see it with people. I saw one the other day, a child standing up on the back seat, holding onto the two front seats while the mother and father were driving down a road. And I thought, if ever anything happened there, that child is through the windscreen or straight into the dashboard, which is it's a terrible thing. So, you know, people, if they understood a little bit more physics, they might be a little more cautious on the road. Anyway, the ball is traveling upwards at the same velocity as the basket. So now if I drop the ball, I know I didn't drop it in this, but if I drop the ball, what is happening? Okay, this is just a precursor in case they don't throw it up. So I have got my basket like that, okay? Now we are standing inside the basket, right? And we are holding the ball in our hands. The basket is going up, which means the ball over here is what? The ball is going up. So then I let go, right? I drop it out of the basket. But the ball is still going to go up before it goes down because I've given it an upward velocity. I'm throwing it up essentially, but in this case I'm not throwing, I'm just dropping it over the side. But it is traveling upwards at the same velocity as the basket. Now in this question, I say I throw it at 3, which means not only is my basket moving at 3, I throw the ball up at another 3, which means I am actually throwing the ball into the air, right? That's the difference. That's what you've got to realize is when we do these, this is why I say the drawing is critical. But as is, to be honest, as is trying to do as many examples as you possibly can so that you can understand the legit, or rather understand the way they ask the question. Let's have a look. Here's ground, and let us say over here, this is where we are in our basket, up there, and we toss the ball out, but we toss the ball, V of the ball equal to 6 meters per second, correct? 6 meters per second, because that is what I am traveling at. Traveling at 3, and I'm adding another 3 to it. So the V of the ball is 6 meters per second, and they tell me I am at, sorry, not 30 meters, I'm at 20 meters above the ground. Right, so now when the ball and the basket pass company, The basket keeps on going at 3 meters per second up. What does the ball do? Let's first of all just have a look at the ball, shall we? I like to split the sections into two. So let us, sorry, I've gone a little bit too far. Okay. Let's just have a look here. First of all, this is the ball. So the ball is doing, and I'm exaggerating it, right, obviously, but the ball is doing this. Where was the ball? The ball was 20 meters above the ground, right? And it had an initial velocity equal to 6 meters per second, correct? Now, in this motion, this projectile motion, what happens? The ball goes up. Here we go. This is where I split it into two. Up and down. I say, right, just looking at the up motion, okay? On the up motion, my acceleration is equal to minus 9.8 meters per second squared. Why? Because the ball is being stopped. What is the velocity here? The velocity at the top, V final on this side is 0. V initial is 6. Then when I'm going to the other side, which we'll do, I'm going to say, right, V initial here is 0 and V final is something totally different. All right? So if we split it into two sections, now, let us have a look at the upside. Let's see what we can do with the upside. Well, let's see. First of all, we've got V initial. I'm only going to look at, let me look at up on this side here. Up. So I say, right, V initial is equal to 6 meters per second. V final is 0 meters per second. Acceleration minus 9.8 meters per second. Delta x, that's how far it goes up. And t, delta t, is how long it takes to get there. Let's just go back to our drawing. All right. What are we saying here? I am saying that delta x is that height, and t is how long it takes to get there. So it's going to go up, delta x, and how long. Those are the only two things that I'm missing on that side. So let's have a look. All right. So let's just solve for those two. And I've done it over here. I say, right, we know that. So basically, we are going to use Vf squared equals Vi squared plus 2a delta x. And what do we? V final is 0. V initial is 6 squared plus 2 times minus 9.8 delta x. And from there, we are going to find that delta x is equal to 1.84 meters, right? So it goes up 1.84, and how long does it take to get there? V final is V initial plus AT, which is V final 0, initial is 6, plus minus 9.8 times t. And we solve for t, and we get t equal to minus 6 over minus 9.8, because the 6 goes to the other side, is going to be 0.61 seconds. Now we go back. We say, okay, all right, I'm going to put you in here, delta x, and that is going to be 1.84, and over here is 0.61. Okay, now I've solved the two bits for the up. Okay, then my next question is to say, right, all right, how high does the ball rise and how long does it take to reach this height? Question B, with what velocity does the ball strike the ground? Well, now we have to look at the downside. We say, right, what's the height there to there? That is 20 meters. How high is it from there to there? That is 1.84 meters. On the downside, acceleration is plus 9.8 meters per second squared. Why? Because it's going to go faster. If you're unsure, always say the downside is plus because the ball's going to go faster. Okay? So then I can go now on the downside. And I can say, what do I know? I know VI is 0 meters per second. V final, we don't know. Delta X, we know. It's going to be 21.84 meters. And delta T, we don't know. And acceleration, we say, is plus 9.8 meters per second squared. And from that, I can now go and say, right, I've done it this side. It's VF squared is VI squared plus 2A delta X. VF squared is 0 squared plus 2 times 9.8 because it's positive, and 21.84. Okay, just check that I got that. And that is going to be V final. Don't forget to take the square root. That's a very common mistake. It's going to be the square root of 2 times 9.8 times 21.84, isn't it? And V final comes out to be 20.68 meters per second. Right? The next thing is they say to us, okay, what is the time of flight? What do they mean by flight time, time of flight? The flight time, quite simply, is the total time that it spends in the air. In other words, if you want to look at it, okay, flight time is going to be equal to time up plus time down. So now I need to work out, okay, hold on, how long did it take to go from the top over here to the ground? Once again, we've got V final, V initial, we've got A, we've got delta X, we just have to find T. So for the down one, I'm just going to continue over here. This is my down. All right. On the down one, we're saying that V final equals V initial plus AT. I'm looking for T. V final is going to be 20.68. Let me just check. Yep. 20.68 is equal to V initial was 0 plus 9.8 T. Therefore, time that it takes is going to be 2.11 seconds. Okay? 2.11 seconds. Okay? You could also have used, if you wanted to, you could have said delta X is equal to V initial time plus a half A T squared, right? We could have done that, right? So what we'd have put in there is then we'd have had the distance, which is 21 point, just check, 21.84, correct? 21.84 is the distance it fell. Initial times time is 0 plus a half times 9.8 T squared, and if you solve for T over here, you will get 2.11 seconds. Right? In other words, if we go back to the drawing, okay, I can now fill in time over here, can't I? The time over here was 2.11 seconds. And we said that the flight time is the time it takes to go up plus 2.11, and the time it took to go up is 0.61 seconds. Therefore, it was in the air for 2.72 seconds. Right? The last part is the question continues, and it says, a Assuming the balloon continues rising at 3 meters per second, how high will it be when the ball strikes the ground? Well, remember the balloon, whoops, sorry, the balloon was at 20 meters up when it discharged the ball. Okay, I know it didn't do that, but there we go. How do we work? How long is the ball in the air for? Well, let's have a look at the balloon going up now, shall we? The V over here is 3 meters per second, and V final is 3 meters per second, right? We are looking for delta X. All right? Well, what are we going to do? It's going to be traveling, the velocity is going to be equal to delta X over delta T, isn't it? So, hang on. We know V is 3 is equal to delta X, we don't know, over delta T. How long is it in the air? 2.72 seconds. It took, you just get this clear, it took 2.72 seconds to do that. Right? So we dropped it here, we threw it up here, the ball went, dim. But the balloon kept going up, didn't it? It didn't stop. We threw it and the balloon did that. While this went, try and do that. It's actually quite, really got to focus. What are we saying is the balloon is carried on at 3 meters per second for that. So delta X, oops, I'm not supposed to be in reading. Okay, I think I'll keep it as black. It's going to be equal to 8.16. So in other words, by the time, here we go, the balloon was here, right, 20, the balloon has now gone up another 8.16 in the time that it took the ball to do that to the ground. So where is the balloon now? The balloon is at 20 is 20. This was initial height plus 8.16. So it's at 28.16 above ground, right? That is that one. Okay. Bear in mind they could also give you total time that it was in the air. Then you just put in what you can find out and solve for the rest. The drawing, once again, is worth every single second that you spend doing it because it is giving you an insight into the problem. The next question, the last question of this, is an energy question, which is a roller coaster. All right, really, the energy problem is very, very straightforward at this stage. This is question 29. And what do we say? We say the roller coaster is shown. It's loaded with that mass traveling at 3 meters. So what do? I'm just going to quickly do this, there, and over there like that. This, whoops, just get that a little bit neater. Okay, so B and D and C over there. This height they give us is 1.5 meters. This height over here is 10 meters. By the way, this piece here, this is very often called your datum, okay, or the reference line you're working with. You don't want to work, you only want to work between there and there. So we've got our car is coming along, and what do we say? A, B, C, D, E, and over here is the station. And over there, that's H, all right? The car is fully loaded with a mass. What do? Put it on the drawing. Mass equals 800 kilograms. It's got a velocity. It's traveling at 3 meters per second. Right, so what's it going to do? It's going to go over the edge and go screaming down. They say the total energy at point A. What is the total energy at any point? What kind of energies have we got? Potential, that's height. Kinetic is movement. That's what we're going to do. That's all we're ever going to do at this stage of the game. We're going to look at it and say, right, potential and kinetic and add them together, which gives us total energy, total mechanical energy. But you're only dealing with mechanical energy in this problem. So I say, right, at A, okay, EK, also if some people call it kinetic energy. What is it? It's a half times mv squared, which is going to be, all right, I'm just going to do it here, a half times 800 times 3 squared, which is going to be 3,600 joules. Joules is energy. Remember the electrical stuff we did? The joules there? All right? Joules is energy. Okay. Now, EP, or potential energy, PE, is mgh, which is 800 times 9.8 times, how high is it? It's 10. So that's 29,400 joules. Total energy is 33,000 joules. Right? That's the total energy. All the energy problems are identical. You're going to work out the initial energy, or you're going to some point where you've got both the energies. Here we go. Oops, let's just get that. So that's what they've said is the total energy at A. That was the first question. Okay. B, they want to know what is the energy over here. There. What's the energy there? What has happened? It had a total energy up top. Let me go and I say 33,000 over here. I'm going to put this in red. Right? I've got E equal to 33,000 joules. Also, that is 33 kilojoules. Remember? 33,000. It means that at any other point, over there or there or there or anywhere, the total of this kinetic and the potential must always add up to 33,000. That is the law of conservation of energy. It cannot be created nor destroyed, merely changed from one form to another. So what do? I say, right, I go to the point, and this is all you do as a recipe, you go to the point where they're asking you for the thing. You say at B. Right? I say, right, EK is going to be a half times mv squared, which is a half times 800 times, do I know V here? Nope. VB squared, which is 400 VB squared. EP here is equal to 8, whoops, let me just write the formula down, is equal to mgh, isn't it? Mass is 800 times G 9.8 times H. H is 0. It's on the deck. There's no energy. There's no potential energy. It is here. It is there. It is 0. So it's lost all the potential energy. All of that has been converted to kinetic. And the total, that plus EP, so therefore I say 400 VB squared, 400 VB squared must be equal to 33,000 joules. And what can I work out from that point? I go ahead and I say at that point, VB is equal to, so I say, then VB squared is equal to 82.5. Therefore, VB is going to be equal to 9.08 meters per second. Pretty fast. Okay. The next question, what is the energy at C? Well, what did we say we did? We now go and we look at C. All right? So we move ourselves to that position. At C, we calculate EP and we calculate EK at that point. And we put those equal to 33,000 again. And we solve for the missing one. Let's have a look at C. Okay, I hope you're doing these with me. What is EK at C? It's a half times 800 times VC squared, isn't it? Okay, so that's going to be equal to 400 VC squared, right? And EP here, EP is 800 times mg times h, 1.5, which is 11760 joules. We add them, E total. So it's going to be 11760 plus 400 VC squared. And then what do? I put them equal to the total energy, because the conservation of energy law tells me to. So therefore 11760 plus 400 VB squared must be equal to 33,000 joules. Therefore, now I solve for VB again. I'm not going to go through that long rigmarole. 7.28 meters per second. All right. The last question, I think, is they say, calculate, oops, sorry, that's velocity at C. My bad. Sorry. I still had VB, VC, and VC is there. Sorry about that. The station can only accommodate a car entering at 5 meters per second. Calculate the height of the station. What did we say? We said, hold on, let's go back to our drawing, okay? Because we've got a new piece of information now. We say, okay, V here must be 5 meters per second. Okay, I go now to E, to the station, and I go here and I work out EP and I work out EP, and we add them to get E total. And we put that equal to 33,000. That's the energy we started with. Okie dokes, let's do that. All right. So I say, right, at the station, in other words, at station, okay, which is point E, I think. Right. What do we say? We say EP is equal to 800 times 9.8 times h, m times g times h. EK is going to be a half times 800, half m times v. Now v, they've told us, is 5. Okay, a half m v squared. So that's going to be equal to 10,000 joules. And EP is going to be 7840H. Correct? 7840H, and 25 times 400 is 10,000 joules. We add them and we get E total at the station. 7840H plus 10,000. And what then do we do with that? We put it equal to 33,000. We say, right, 7840H plus 10,000 must be equal to 33,000. Take that to the other side, subtract, and divide by that guy, and you get the height equal to 2.93 meters. Okay, 2.93 meters is the station height. Okay, if it is any lower than that, right? If it's any lower than that, it means that the car's going to come in too fast. Right? If it's higher, it can be higher than that, then it'll come in slower. Okay, so there we go. Obviously, I've tried to encapsulate as many different types of problems and gone through as many as I possibly can in the short period that we've got. As I said, I'm going to do more for all the grades, and with feedback from yourselves, from other people, and so forth. We'll develop more and more of these exam prep things. We'll add questions in and so forth. And obviously, as the syllabus changes, we'll add that to it as well. But once again, as I always do at this point, thank you very much for watching the videos. I appreciate it. I love doing this. I really do. It's quite a passion of mine to hopefully bring physics and chemistry and maths into people's lives. And I really want to wish you everything of the absolute best for your midterm tests, whatever you're doing, and for your finals. And hopefully, who knows, we'll see you in grade 11 and grade 12. And we can carry on working together as a team. And you can even let me know how it's going through the emails, etc. But please, good luck. Remember, learn the definitions, law of this, law of that, everything else. I know, boring, but we got to do that because those are the marks that you get. And what's the last thing we do with physics? Do the drawing, guys. Put the information as you solve it, put it back on your drawing. Circuits, these, everything, you put it back on your drawing. Cheers, good luck, and thanks again. Bye.